Welcome back, everyone, for another deep dive. This time, we're taking a look at Android malware,
Ooh, exciting.
but with a bit of a twist.
Yeah.
It's not just about, catching the malware.
Right.
It's about making the systems we use to catch it more secure.
That's interesting.
So get ready, because it's going to be a fascinating one.
I'm all ears.
Perfect. So it's kind of like, when you build a security system for your house, you don't just put in a fancy alarm and call it a day, right?
No, of course not. You got to think about how someone might try to get around it.
Exactly. Like, where are the weak points? How could they exploit it?
You got to be one step ahead.
Exactly. And that's the kind of thinking we need when it comes to machine learning security.
Makes sense.
And the paper we're diving into today really dives headfirst into this whole concept.
Oh, cool.
It's called Yes, Machine Learning Can Be More Secure. A case study on Android malware detection.
Catchy title.
Right. And it's by Ambra, Demontis, and a whole team of experts.
All right, so what's the main idea?
Well, they really challenge this assumption that if we use machine learning, it's going to be automatically secure.
Yeah, I guess that makes sense.
Especially, when you're dealing with something as slippery as malware.
Oh, yeah, malware is always changing, always adapting.
Exactly. It's like that friend who's constantly changing their look.
Trying to stay ahead of the trends.
Right. And how do you even begin to build a system that can actually keep up with that?
Good question. That's where Drebin comes in.
Drebin.
Yeah. It's this Android malware detector that uses static analysis.
Okay, static analysis. So it's like...
It's kind of like a detective, It can profile an app without even having to run it.
So, what kind of clues is it looking for? What does it mean to profile an app?
Well, Drebin digs into the app's insides, you see. It looks at the permissions it wants,
Okay.
the API calls it makes, even any network addresses hiding in the code.
Oh, wow, that's pretty deep.
It is. And then it takes all that info, all those clues, and turns it into what we call a feature vector.
A feature vector.
Yeah.
What's that, like a digital fingerprint?
Yeah, that's a great way to put it.
So each app has its own unique fingerprint.
You got it. And that's where the real magic happens. Drebin uses this thing called a support vector machine, or SVM for short.
SVM. Okay, I'm listening.
Basically, it's this powerful tool that learns from a massive database of apps, both the good guys and the bad guys.
So it's learning what a malware fingerprint looks like versus a harmless app.
Exactly. It's like a detective studying mugshots, learning to spot the bad guys.
And then it can use that knowledge to catch new malware.
You got it.
Okay, so this sounds pretty straightforward. What's the catch?
Well, remember what we said about malware always evolving?
Oh, right.
Well, the attackers are evolving too, and they're not just trying to hack into systems.
What do you mean?
They're attacking the algorithms themselves, the very tools we're using to catch them.
Whoa, hold on. Attacking the algorithm itself? That sounds way too clever.
It is. But remember those fingerprints we talked about? Imagine the attacker, subtly tweaking their malware's fingerprint, making it look more like a good guy app.
So they're trying to trick the system, basically.
Exactly. Maybe they sneak in some harmless permissions or tweak some API calls.
And then Drebin wouldn't even notice.
It might just slip right past.
That's sneaky. So how do you even test for something like that?
The researchers had to think like the attackers. They created something they called an attack framework.
An attack framework?
Yeah. It systematically tests different attack scenarios.
Okay, so walk me through this framework. What kind of scenarios did they cook up?
Well, they start with a baseline. They call it zero-effort attacks.
Zero effort? So like the laziest attacker ever?
Pretty much. They just use regular, unmodified malware to see how Drebin handles the basic.
Makes sense. So what's next?
Then they get a little fancier, testing commercially available tools like DexGuard.
DexGuard, what's that?
It's a tool developers use to make their code hard to reverse engineer, kind of like scrambling it.
So it's not meant to fool machine learning, but...
But it might change the app's fingerprint enough to throw the detectors off.
Interesting. So did it work?
Well, they found that DexGuard does provide some protection, but it's not foolproof.
Okay, so what about the more targeted attacks?
Things get really interesting there. They simulated attacks where the bad guys have more and more knowledge about the system.
Okay, like what?
They looked at mimicry attacks, where malware is carefully crafted to resemble good guy apps.
So they're really going all out to blend in.
Right. Then there are limited knowledge attacks, where the attacker knows the learning algorithm and can train their own model to test against.
They're basically building their own mini Drebin.
In a way, yeah.
That's starting to get a bit scary. How much could these attackers potentially know?
Well, and then there's the worst case scenario, the perfect knowledge attack.
Uh-oh. That sounds bad.
It is. This is where the attacker knows everything about the system, the algorithm, the training data, the whole shebang.
Yikes. Like giving them a blueprint and saying, okay, try to break this. I'm guessing they didn't just leave us hanging with that terrifying thought, right?
Of course not. They came up with a possible solution.
Okay, I'm all ears.
It's called Secure SVM, or SecSVM for short, a souped-up algorithm built to be way tougher against these attacks.
Secure SVM. Interesting. So how does it actually work? Does it, like, build a wall around the algorithm?
It's more subtle than that. Remember how we talked about attackers messing with specific features to make their malware look innocent?
Yeah.
Well, SecSVM makes those features less important in the decision-making process.
Ah, so it's like spreading out the risk.
Exactly. It's like trying to sink a battleship. Instead of aiming for one big weak spot, you'd need to poke tiny holes all over it.
So you're forcing the attacker to work much harder.
Precisely.
I like it. But the big question is, does it actually work? Does Secure SVM really hold up against these attacks?
That's where the experimental results come in, and trust me, they're eye-opening. But before we jump into that, maybe let's take a closer look at those attacks and how they were tested.
Yeah, okay. Let's do that.
So, to really get a handle on how these attacks work, let's look at some examples. The researchers highlighted some specific features in the paper, the ones attackers might target.
Oh, okay. Like what?
Well, one of them is related to a suspicious API call. It's suspecalls.android telephonexems message, right? RO get display message body.
Whoa, that's a mouthful. What does
Yeah.
that even mean?
It's basically a way for an app to access the content of your text messages.
Oh, okay. Yeah, that's definitely something you'd want to flag.
Exactly. And an attacker, they might try to hide this call or, make it look less suspicious to avoid detection.
So they're trying to cover their tracks.
Yeah, exactly.
Yeah.
And another example they mention is reperm.android.permission.uec credentials.
Okay, and what's that one about?
This one refers to an app requesting permission to use your login credentials.
Again, pretty suspicious.
Yeah.
So how does SecSVM, how does it actually make it harder for these attackers to mess with these features?
Well, think about it. Traditional machine learning models, they might give a lot of weight to these individual features.
Okay.
So if an attacker can, successfully manipulate them, well, it could have a big impact on the classifier's decision.
Right. Makes sense.
But SecSVM, it kind of spreads the importance more evenly across many features.
So instead of having a few big targets, you've got, like, a whole bunch of smaller ones.
Exactly. It's like trying to camouflage yourself in a forest. You wouldn't just change the color of one leaf, right? You'd have to change every single one.
That's a great analogy.
Right. So it makes the attacker's job way harder.
And this brings us back to something we kind of touched on earlier.
Oh, what's that?
The whole sparsity versus security trade-off.
Ah, yes, the classic dilemma.
Right. It's like choosing between a sports car and a tank.
Exactly. So in machine learning, you see a sparse model. It's like that sports car.
Nimble, efficient.
Yeah. It relies on just a few key features to make decisions. This also makes it more vulnerable to attack.
Because if the attacker figures out those key features, they can mess with them.
Bingo. They can exploit those weaknesses and throw the whole system off.
So Secure SVM, by spreading the importance, it's more like the tank then.
You got it. Slower, maybe. A bit more resource intensive.
But way more difficult to take down.
Exactly.
And so this trade-off, is this something that, like, machine learning people always struggle with?
All the time. There's no easy answer. It really depends on what you're trying to do, how much security you need.
Right.
But here's the thing. This paper, it hints that this trade-off, it might not be set in stone.
Wait, really? You mean we could have both? The speed of the sports car and the strength of the tank?
Maybe. It's like, maybe we can develop systems that can adjust their sparsity on the fly based on, how dangerous things seem.
So like a machine learning chameleon, adapting to the environment.
Exactly. That's the exciting part.
So let's get to the results. How did Secure SVM perform when they actually put it to the test? Did it live up to the hype?
Let's see. First off, they looked at how the different classifiers did against those, basic malware samples, the zero-effort attacks, remember?
Yes, a lazy attacker.
Right. And what they found was Secure SVM, it held its own. It was just a tiny bit less accurate than the original Drebin.
So not bad for adding an extra layer of security.
Nope. It's when you look at those tougher scenarios that things get really interesting. For example, In that perfect knowledge attack, remember the one where the attacker knows everything?
Yeah, the scary one.
They found that Drebin's accuracy, it just plummeted after only 2 features were changed.
2 features? Seriously, that doesn't seem like a lot.
I know, right? It really shows you how vulnerable these systems can be. But here's the kicker. With secure SVM, it took something like 15 changes to achieve the same level of evasion.
Wow, that's a massive difference.
It is. And you got to remember, the more changes an attacker has to make, the higher the chance they'll break their malware and make it useless.
So it's not just about making the system impenetrable, it's about making the cost of attack way too high.
Exactly.
Okay, so secure SVM did well against the perfect knowledge attack. What about the other ones, like the limited knowledge and the mimicry attacks? Did it hold up there too?
It did. It consistently did better than the other classifiers, showing a much slower decline in accuracy as the attacker made more changes.
Okay, so it's looking pretty good.
And even in those mimicry attacks where the attacker's trying to, blend in with the good guys, secure SVM was still much tougher to fool.
All right, so I'm starting to see why this secure SVM is such a big deal. But how did they actually measure all of this? How did they compare the performance of these classifiers?
Well, they used this technique called ROC curves. Stands for Receiver Operating Characteristic.
ROC curves. Okay, I think I've heard of those. But to be honest, they always kind of make my head spin a bit.
Yeah, they can be a little tricky. But think of it like this. You got a security guard, right? Standing at the entrance of a building. Their job is to spot any threats and keep them out. The threats, in this case, are our malicious apps.
Right, and the building is our Android device.
Exactly. Now, this guard, they can be really strict, checking everyone super carefully.
Okay.
They might catch every single threat, but they might also accidentally turn away some harmless visitors.
So like high true positive rate, meaning they're catching all the bad guys, but also a high false positive rate, meaning they're flagging good apps as bad.
Exactly. But if the guard is too relaxed, well, they might let some threats slip through, but they'll also be less likely to bother those harmless visitors.
So it's a balancing act.
It is. And that's what the REC curve helps us see. It shows us all the possible ways we can set up our security guard and lets us pick the best one for this situation.
So what did the ROC curves show for this research?
Well, they showed that secure SVM, it kept a much better balance than the other classifiers, especially when under attack.
So even when facing these clever attacks, it could still find the threats without too many false alarms.
That's right. And what's really cool is that it does all this without knowing anything about the specific attacks beforehand.
It's like having a security guard who's ready for anything.
Exactly.
Okay, so secure SVM sounds pretty awesome. Is this the end of the story? Is it like the ultimate solution to all our machine learning security problems?
Well, the researchers themselves say that this is really just the beginning.
Oh, there's more.
Definitely. Secure SVM, it's a big step forward, but there's still a lot more to figure out. So where do we go from here? What's next?
Well, one thing they suggest is, exploring these things called nonlinear classifier.
Nonlinear classifier. Okay, I'm listening.
Remember how we talked about those SVMs, drawing a line to separate the good apps from the bad?
Yeah, the good old fence analogy.
Right. Well, that line, it's a linear boundary. But what if we could, make it all curvy and complex, Make it harder for those attackers to manipulate.
So instead of a simple fence, it's like a maze. Exactly. That's the idea behind nonlinear classifiers. You add all this complexity and it just throws the attackers off balance.
So they can't just tweak a few things and slip right through.
Right. They got to work a lot harder to figure out the system.
That's pretty cool. So are nonlinear classifiers, are they like the next big thing?
They could be. But there's another idea in the paper that I find even more interesting. They talk about assigning different levels of robustness to different features.
Different levels of robustness. Okay, break that down for me.
Imagine you can tell the classifier, hey, this feature over here, this one's super important, make it really tough to mess with.
Okay.
But this other feature, it's helpful, but it's not as critical. It doesn't need to be quite as strong.
So it's like having a security system with different levels of protection for different areas.
Exactly. And this way, you can create systems that are even more adaptable, They can handle a wider range of attacks.
It's all about staying one step ahead of the bad guys.
Right. It's not enough to just react to attacks. You got to anticipate them.
It makes you think about the whole evolution of cybersecurity.
Yeah.
It's this constant back and forth.
It is. And as we rely more and more on machine learning for security, we got to be ready for those algorithms to be targeted.
But the good news is we're not helpless.
Not at all. This research shows we're making progress. We can make these systems stronger and more secure.
That's reassuring. So before we wrap up, let's bring it back to our listeners. What are the big takeaways here? What do you want them to remember?
Well, the main thing is, machine learning security, it's a challenge, but it's one we can definitely tackle. We just got to be aware of the risks and, build security into these systems right from the start.
We can't just assume that if it's got machine learning, it's automatically safe.
Right. We got to be smart, got to be proactive.
And never stop learning.
Exactly. This research gives me hope. It shows we're moving in the right direction.
To all our listeners out there, next time you hear about machine learning being used for security, don't just take it for granted. Ask questions. Be critical. And remember, the future of security, it's in our hands.
Knowledge is power. The more we understand, the better we can protect ourselves.
Couldn't have said it better myself. That's all the time we have for today. Thank you all for joining us on this deep dive. Until next time, stay curious, stay informed, and stay safe.